First, thanks for the invitation. So today we are going to talk about something in the pre-training algorithms for NLP. So just as Jiajun mentioned, so like we have a lot of large-scale pre-training in the NLP system recently. So this actually pushed the NLP field quite a lot. So today I'm going to introduce a little bit a brief history of like pre-training in NLP first. Then I will follow up by two other recent research that has been done in my group. And we will start with a brief history of this pre-training algorithm. So recently, there has been news about GPT-3 and DALL-E. So GPT-3 is a very large pre-trained language model. So it actually gives astonishing performance in a lot of NLP tasks. So for example, if you do zero-shot learning, so basically you just type translate English to French, and then what's cheese in French, then the model will give you the answer. So it can do few shots, it can do one shot, zero shot, all this like astonishing abilities of generalizing the language. So on the right side is DALL-E, where like it's a joint training of NLP and computer vision. So basically you have input such as an armchair in the shape of avocado. Of course, nobody has seen this thing before. Then like if you pre-train that with the image generating system, then you get the following images down below, which is like quite impressive. Like it's kind of a designed style chair there. So basically it gives you the ability to control the image generation through language. So the trend of pre-training in NLP actually starts from what we call BERT, bidirectional encoder representations from transformers. So this model actually given by Google, it's actually refreshed the leaderboard of multiple natural language processing tasks, including question answering and natural language inference. Probably a few weeks, it gives a new result. So began by this, the performance of the deep learning neural language models has been surpassed the human performance, and it actually achieved quite a lot of useful applications as well. So actually from 2013 and to 2014 in natural language processing, we have something called word vectors, actually word to vect and glove, these kind of word typed embeddings. And then we move towards the pre-training, large-scale pre-training algorithms, which we called contextualized word representations. So starting from Elmo to BERT to GPT-2 to GPT-3, it's basically has been done within the past 3 years. So starting from 2018 to 2020, so the performance is like growing fast, and the parameter size is also growing exponentially. Like Elmo only have 90 million parameters, while GPT-3 has already like 175 billion. So I have a small figure downside. So like GPT-3, it is probably a dinosaur sized model. If you look at GPT-2, which is like only 1.5 billion parameters. So the training corpus is also grow a lot. So like 11 gigabytes is the starting point, and we now reach 570 gigabytes. This is actually, after a very large scale pre-processing from even larger language corpus. So this is like exponential growth. So the lesson we learned from there is the usefulness of large-scale training. So large-scale computation is really, really useful. On the left side, I list a few like famous models written here. So you can see like this is a log scale thing. So it's a clear exponential growth of computation. If you look at these models like AlexNet in maybe 2013 to AlphaGo Zero 2 years ago, it's a clear exponential growth. So, but we argue that only large scale is probably not enough. We have to do high quality computation as well. So that's the following two research has been focusing on. So the first one is focusing on the objective function. So basically we use pre-training algorithms like what kind of objectives we should choose. This is clearly unsupervised or semi-supervised learning tasks. So what objective functions we can choose for this kind of large scale computation to reach the high quality. And the second one is the structural inductive bias. So as we know that language is always a domain science. So it's compositional. It's not only left to right. So it's probably like this river valley thing. So it's probably first give you a noun phrase and then attach it to a propositional phrase. So this kind of composition is not left to right. So how we handle this kind of structural inductive bias in our model. So part one is a mutual information maximization perspective of language representation learning. So if we see the BERT pre-training objective, it's actually pretty simple. So it's basically called masked language model plus next sentence prediction. So MLM and NSP. So masked language model is basically you have a sentence there. So I feel like eating blah, 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 and what do you want? So we here just randomly mask two words, and the encoder, which we use transformer, you can use whatever, you can use LSTM. So the task is basically to predict these two words, what these two words are. So probably the first one is fruit, and the second one is almost sure is a do. So this is task one. And task two is basically next sentence prediction. So we ask the question that if the second sentence is a natural follow-up of the first sentence, or it's just some random noise, we add 50% of the random noise in the pre-training stage. So this is a binary classification. Just ask if this is a natural follow-up, it's a next sentence. So we know this pre-training task. This is actually quite simple, but it doesn't tell us a lot more of like what kind of objectives that we should choose in pre-training and why this kind of like pre-training objectives actually works at all. So we review this from the perspective of mutual information maximization. So mutual information actually models the event A and event B. So knowing something about event A, can you reduce the uncertainty of event B and vice versa? So this is a symmetric one. So HA minus HA given B. So this thing is actually hard to optimize in terms of like choosing it as an objective. But luckily, we always have this lower bound, which we called info NCE there. So here we have A and B are two views, and B is basically negative samples. So negative samples, we sample from a distribution of B tilde. So we actually want to upper the score if A and B are natural pair with each other. If B are negative samples, probably one thing and another view, then we will downscore that. So that's the intuition of this objective function. It's quite like quite similar to the cross entropy one, where B is just a uniform distribution. Basically, we sample everything from the possible space. So here, F, A, and B is just a scoring function, scoring the pair of views. So A is one view and B is another. So knowing one view, can we reduce the uncertainty of another view? So that's what behind the BERT. So BERT actually is one view is the contextual representation of the masked sentence. So it's a corrupt context of word I. So the B view is actually the word itself. So basically knowing the context of this word, we should reduce the uncertainty about this word. That's the whole intuition behind that. So here I use the red color as view one and blue color as the true view two. We also have like these white little boxes there, which is actually we can see them as negative samples. So we want to increase the score if we find a red and a blue pair. If we find a red and a white pair, we want to downscore that thing. So next sentence prediction is also in the spirit of this thing as well. So we have two sentences and we have encoding of the first sentence, which we have it using a transformer, and we have that as a red view. And we have a lot of things, a lot of other sentences from the same batch. We call them the B tilde space. So some of them are correct, which we label them as blue, and some of them are just random sentences, which we have them as white. So we want to increase the score of the true pairs and decrease the score of if it's not pairing up together. So this thing actually called global NCE. So we, at first, this thing is a binary classification, which we call local NCE. But if we move it to the space of global NCE, it's mathematically equivalent to each other. So knowing this, what can we do? So we can use this view to design like better objectives. So we taken the inspiration from deep learning, deep informatics, which is from computer vision. So the view there is basically you have a figure, and then you have that global feature, which is like you're taking all the things and encode that into a vector. And you also have local feature, which is like you're taking some parts of this figure and then map it to a local vector we call local feature. So of course, we have the local feature taken from the same image of the global feature. We also have like local features taken from a different image. So we here have the real pairs and the fake pairs. So the real pairs is the ones we want to increase the score, and the fake pairs, of course, we want to downscore that. So what's that in natural language processing? So we have the global view. So the global view is basically the sentence itself. We also have the local view. The local view is probably one phrase of the sentence. So like several words up together, like the United States of America or the University of Hong Kong. So these kind of phrases, we have the local embeddings. So remember that originally in BERT, we always only have the view B as a word itself. So we are not satisfied with that. We want to have some kind of a segment embedding for the text. So this is what we do. So we have this local view, which is like a small phrase, and we have the global view, which like the other context of this sentence, and we want to pair them up, pairwise them, and like upper the score of the real examples. So we use the same encoder for different things. We use the same transformer for the phrase. We also use the same transformer for the global view, which is like we think a good representation, transformer should basically work both on the local side and also on the global side. So that's what we do. So in the end, we call this loss info word, where we have this mass language model and work with our new loss, which we call DIM. So we have something targeting the small word representations. We also have something targeting the phrase level representations. So we tried that on different tasks. One is reading comprehension. This is like basically you have a passage and you have a question. You want to answer this question by selecting some segment from the passage. Clearly, the segment representation means a lot in this task. So we compare with original BERT and we use the BERT NCE and our info word. We can see that on base model and large model, our performance always better. So base is the model with fewer parameters. So the large one is the original BERT with like 100 and some million parameters. So we can see the nice curve here where we find that the DIM loss when it has this sweet spot. So basically it has to find a trade-off between the representation abilities between the word level things and the phrase level things. You want to have like 0.6 probably in different tasks that you can tune this hyperparameter. So we also tried that in natural language inference tasks. So GLUE, which we have like a lot of classification tasks like similarity, paraphrase, inference, and sentiment analysis, all of this. So we also can see like the improvements in these models. So here we know that we probably should design our objectives for pre-training better, because like we want to consider what the downstream task really wants. So in our case, we really show an example of doing this by incorporating the segment level information into our model. So we also find the field like has a lot progress in terms of the encoders. So for example, we have the transformer, we have the XLNet, which a lot of changes happens on the view A side, not view B side. View B side, we always choose the word itself. So we argue for some space of improving the representation from the view B. So like, can we choose phrase? Can we choose sentence? Can we choose whatever things we care in the downstream applications to form the view B and like to form more interesting objectives in pre-training? So in part 2, we want to talk about syntactic structure distillation pre-training for bidirectional encoders. So in this thing, the key question we want to ask is, can we design an even better masked language model that not only works well at scale, but also integrates our prior knowledge about compositionality, of natural language? So why this is a good idea? So natural language, as I said before, is always compositional. So like blue table, like you first form the blue table into a whole meaning before you put it into the sentence. So this is kind of things happens in language. It's compositional, it's hierarchical. You can call it from whatever language perspective you have. So we have some surprising failures in BERT that because we ignore such structures. So we have the context here, Richard borders Elizabeth, and the question is like, who is Bernard? This is like a really, really simple question. I believe no human beings can make mistake in this. So, but the correct answer is Elizabeth, but the model actually predicts Richard because it ignores the syntactic structure inside this thing. So this kind of sequential objectives works well in terms of the structural mistakes. So we want to do two things. One is we want to have this structural bias into our model, but like another thing is we also don't want to sacrifice the large scale pre-training. So like a lot of structural biases are very expensive, so they cannot probably even batch. So how can we inject these kind of biases, but still like preserve the high efficiency in terms of large scale pre-training? So we do this by knowledge distillation. This is probably the first thing we will think in terms of doing such things. So we have a teacher model, which is, we call it RNNG, Recurrent Neural Network Grammar. And we have a student model, which is BERT. It is large scale, but it doesn't consider the hierarchical structures. So can we like have this like more difficult model, more harder to train, harder to scale model, which understand explicit syntactic structures to teach this student model to learn more about how language is composed. So the teacher model RNNG basically, instead of read a sentence from left to right, it actually build a bottom-up recursive composition function, where like the example here is it first build a representation of the river valley before it attach this representation to of, and then form a propositional attachment, so of the river valley. So this kind of thing. So it actually build up this computational graph bottom-up recursively. So what we do is we use this model, we train it on 3% of the whole BERT data, which includes the book corpus data and plus some Wikipedia data. And it takes us 3 weeks of GPU. So this thing like as we see, it's very, very, very expensive. So then we use the model to label the whole thing, to label the whole full training set. And then we have like what the RNNG thinks about the distributions of the word. And then we distill that knowledge into BERT. So this is the setting. And the objective function is simple. We just use Hinton's standard knowledge distillation and objective. So the intuition here is like the second part is basically the student distribution. So what the BERT students thinks the mask word should be. And the first part is the teacher distribution. It's like what RNG's approximated posterior distribution thinks the mask word should be. So we can see that the teacher is teaching through this objective function. So we evaluate our task in two different group of settings. One is where we need explicit syntactic information, and the other one is we don't explicitly need that. So the first one including parsing, and second one includes like semantic role labeling, which is like quite important in terms of dialogue systems and robotics. So it also have coreference resolution, where like, you know, the task is the first sentence has some pronouns like he, she, it, what it refers to. So we want to go back. So clearly the syntactic structures helped in those kind of tasks, but actually, you know, don't explicitly need that. So we find that we improve the performance of the parsing task and reach the new state of the art in using BERT. So this is the dependency parsing we win in terms of the in-domain task, which is like news while task. We also like generalize better in terms of the out-domain task. So we also try the thing on semantic role labeling. It achieves like almost 10% relative error reduction and reach the new state of the art. So we also try that in coreference resolution. So the thing is actually the same story here. We achieve 2.6 relative error reduction. And we find that in the low data setup, actually the syntactic bias helps to improve data efficiency. So some reflections. So it actually is quite surprising that this works because it's quite simple. So we improve BERT by learning from an RNNG teacher. So the RNNG teacher compares with BERT what it has. So it only trains on 3% as much data. And it only has maybe, it only has 1/5% of the number in terms of number of parameters. So it's quite small model, but the only thing it did better is like it knows for syntactic structures. It has these syntactic inductive biases inside it. So it is also like less well optimized implementation than the transformers, but only because it has this syntactic inductive bias, the hierarchical inductive bias, it actually helps the BERT model, the student model, to learn better. So we confirms the benefits of syntactic biases for large-scale models. So human children can learn syntax of language with very few examples. So human children probably can only see like 3% of BERT training example in their early ages, but they will already know like how to generalize the language performance. So this actually starts something where we want to inject such kind of structure biases into our large-scale training models that can still works well. So that's what we call the high-quality computation. We think this is a promising and relevant direction in our future works. So in retrospect, we know that in pre-training algorithms, large scale is really the key factor that makes it work. But we also want to argue that we also need to do high quality computation there. So we start that by doing two things. One is like, can we have better objective functions which encode better representations for different parts of language, like segment structures? So we also have another thing is like language is always compositional and hierarchical. So can we induce this kind of structural biases in our pre-training models to achieve better performance? So that's the second part of the talk. So that concludes the talk today, and I will thank my colleagues to this kind of works. Yeah, thank you.